Hey, what's up, guys? Chung here again. And this time, let's take a look at another medium level LeetCode problem here. Hmm, it's called it's number 416. Partition equal subset sum. Okay, and you're given like a non-negative, only positive integers. Okay, and it asks you to partition these two subsets. This partition this array into two subarrays, uh, which each of the sum of the subarray are the same. Okay, for example here, so with this 1, 5, 11, 11, so this array can be partitioned as 1, 5, 5, and 11, both of whom, both of them have the same sum, which is 11. And for example, this one, 1, 2, 3, 5. For this one, there's no way we can partition this one to this array into subarrays with the same with the same sum. Okay, so mm, so how can we solve? So what's the so this problem? It's I think if you think it a little bit more, it's actually a very typical uh 0, 1 knapsack problem or the 0, 1 backpack problem. Why is that? Because mm, since it's all positive numbers, okay, and that's which means the total sum is always increasing, right? So for this case, for example, this one, the total of this sum is what? It's 22, right? It's 22. So this problem, basically, if we have a total sum here, and all we need to check if there's any subarray, right? If there's any, actually, it's not a subarray, right? Um, yeah, it's a subset because the sequence could be different, right? Basically, so now the problem converts to if there's any subsets whose whose sum equals to the 22, the half of the 22, which is 11. Okay, and as long as we find a one subset whose sum is half of the total sum, and then we know the other half is the same. Okay, and since all the numbers are the are positive numbers, so there won't be any case. Let's say if in case we have 11 here, so there won't be a case that this one subset will use all the numbers because each of them is integer. It's a positive integer. That's why we can make sure once we find one subset whose sum is half of the sum, there's still some other numbers left for the other half of the subset, right? And and then actually this problem is converted to a 0, 1 to a 0, 1 knapsack problem, right? Because all we need is that's basically this half of the sum will be our capacity, right? Capacity. And these numbers, okay? The total numbers is going to be the items, right? So this is going to be the items. So now we just need to find out from these items, can we select, can we basically use 0 or 1, right? 0 or 1 numbers whose sum is 11, is exactly to the 11, right? I think this is a little bit different because, for the, tra the traditional or the normal K knapsack K the backpack problem, it's a it's the it's the max it's the you can use up to this capacity, right? Not the basically you can use until this capacity, but you can also use less than this capacity, right? But in our case, it has to be the same. It has to be the same as this capacity. It cannot be smaller than this one. Okay, so that's a bit different. And so how do we handle this different variation here, right? If you remember for the 0, 1 classic backpack problem, when we define the DP, right? So we define the DP here. We first we initialize everything to equals to 0, right? We initialize everything to 0. That's yeah, that's when we that's how we get the biggest value up to these capacities. It could be smaller, or it could be the same capacity. And if we want to get the max value only for this capacity, that's why when we that that so a changes we need to make is instead of initializing everything to 0, we only initializing the DP 0 to 0, and for all the else DPI we initialize them mm, to negative biggest number. So that's a change we need to make here because we want to make sure, right? Because we want to make sure anything that we get, right, is from the 0. Because anything else, it's not actually will not be the exact capacity if we are getting the values from the DPI. I is not 0, right? That's why we basically will initialize this uh, the other elements to the minus max number here. So and then when it comes to this problem, it's the same thing, right? So in this problem, we don't need to store the value here. All we need is a true or false flag. Okay. So same thing here. So for this one, the DP0 will be true here, and all the other DPs will be false. Okay. So that since we're only setting the DP0 to be true, right? And then when we reach to the end, the last one, which is the n, right? Then we know as long as this one is true, then we know, okay, so this one must have come from the DP0. Okay. Mm, okay, so same thing for this problem. So for this like a k-knapsack problem, I'm gonna use the 2D two-dimensional DP first, and then I'm gonna improve the basically compress, flatten the 2D array into 1D. Okay, cool. So for 2D array, right? And yeah, so first let's do a sum here, right? Since we need to get the total capacity first, which will be the total sum here. Some numbers. Okay. So and then we're gonna have like a capacity. I'm gonna just use a C here. C equals to total divided by 2, right? But I think one thing we might want to check here is the since we're using the the integer division, right? I mean, if the total number is an odd number, right? For example, this one, right? So the total, what's the total for this? Total is the 3 plus 8 is 11. Okay. Since 11 cannot be divided by 2, right? There will be a remaining number. So that's why we can simply do a check here. Basically, if the total, right, mod by 2 is not 0, we simply return false, right? That tells us there's no way we can divide it because it's not an even number. So after this check, now we can make sure, okay, now the total is the even number. Now it's safe for us to divide it by 2 to get our actual capacity for this backpack problem. And okay, and then we're gonna have like an n here, right, for the numbers. So for the 2DP problems, we're gonna need numbers here, right? Length of the numbers. Now it's time for us to initiate the 2D DPs here. Okay, at the beginning, everything is false. Okay, and the second dimension will be the total, the capacity, right? And then the first dimension will be the numbers, the numbers of the elements, which is the n plus 1 here. Okay, so that's, and like I said, so the first one, we need to initialize the first element to be true. So basically the dp00 will be true. So what does this mean? It means that, and so just follow the definition from the backpack problem, the knapsack problem. So dpij means uh with the first items, the total, I mean, to get with the current capacity, what's the value? Okay, and for this problem is the without any numbers, right? Without sorry, with so for this problem, dpij stands for with first items. So this it's not items, it's like first ith numbers, and can it form to the j exact j number, right? So basically it's going to be either true or false, right? So that's how we define the DP here. Actually, the K knapsack problem, the template itself is only providing you a way of emulate all the all the possible combinations. And other than that, it's for each problem, the definition of DP will be slightly different. And for this problem, it's just this dpij will be standing for the true or, the value will going to be true or false. So, and when it comes down to the base case 0, 0, it means that with zero numbers, can it form to 0, right? Which is true, right? Because we don't need to do anything, and the value is true, because if there's no numbers and the target number is also 0, it's it's true. Okay. And now now it's the normal 2D 0, 1 K knapsack template. Basically, the first one we loop through the numbers, the items. In this case, it's gonna be the 1 to n plus 1, right? That's the numbers. And then we're gonna have like numbers. We can do it. And the second one will be the the capacity, right? The capacity is from 0 to a c plus 1. Okay, and then the first case for 2D, right? It's always always not taking the current item, not to take the current item or the number in this case, right? So which will be result to a dpi, will make the dpij equals to dpi minus j, right? Basically, we're not taking this number. That's when we need to use the previous state, but with the same capacity. Okay, and now for the second one, right? And we're gonna, if like same thing, if the j is greater than the what? Then the numbers I minus 1, okay? Then the dpij will become to the sorry, the so in this case it's gonna be either true or false, right? Because we want to check between all these things if anything is true or false. So actually we can just do this, and yeah, since we already assigned, because here I'm just following the original template here, and in this case basically we want to check between all those two options if we can still get a true or false. So which means we have to do this one or, right? You know, for the other scenarios, we either do a max or minimum, right? Comparing with the current one with and then the rest of it. But now here we're doing we only get the true or false. That's why I'm gonna use a or here, right? And the same thing for the second one. So the second scenario here is we choose to use the current ith, we choose to use this ith number or item. So that makes the dpij will be convert to dp I minus one. Still it's I minus one because remember, so I think I talked with you guys, briefly talk about this one, why we need to use I minus one here, because it's a 0, 1 case, right? So basically we have to rely on the previous state, which we never used the ith item, okay? Here, and if we choose to select to use the current number, and then the previous state will be the j minus, right? J minus numbers I minus 1. That's why I do a check here, right? Remember, see? So because we otherwise this j minus to nums I minus 1 will be what? Will basically be inactive value, which will be an invalid state, right? Yeah, and then yeah, see? So there's nothing else. Yeah, so yeah, that's the basic to the uh, 0, 1 knapsack problem template. And in the end, we simply return what? Return the DP, the last element, which will be the N and the capacity. Okay, right? That's basically the true or false. Mm, yeah, I think let's try to run this code here. Okay, so the test case passed. Let's try to submit it. Cool. Yeah, basically it works, right? Yeah, just very classic uh 0, 1 knapsack problem. All you need to do is we have to the only thing you need to make to be careful is to be no to pay attention is you have to be able to somehow convert this like problem into a backpack problem, and you have to be able to figure out to realize that we just need to find half of it, right? So once we find the half of it, we don't need to care about the other half. Then it converts this two subsets problem into a one subset, and the one subset problem is a typical scenario of the backpack problem, right? Okay, and yeah, so like I said, we can compress this 2D DP array into one DP, right? As you guys see here, so the dpij only relies on the dpi minus 1 dpi minus 1, right? So for the j we can't, because for the j we still need to loop through everything. So in that case we can simply just you know remove the first element, the first array, which will be this n plus 1 array here, right? So I'm going to remove this first array and here, right? And we remember we still need to do this the first this two nested loop. But remember, I think I have already talked about this one. So in order to make this 2D into 1D, so the way we're looping through the we're doing the second loop, it has to be from the biggest to the smallest. So why is that, right? I'm gonna uh, explain that one more time. Notice here, we only want to, when we calculate the dp I and j here, right? We only want to use the state from the previous state. Previously, which means dp I minus 1 state. Okay, we don't want to, because, right? And if we are still, if, okay, let's say if we're removing this first state, right? Let's say if we are removing the first element, the first dimension here, basically, we don't have that the first dimension anymore, right? So basically, both the I minus 1 state and I state will be using the same 1D array, right? And how can we make sure when we calculate the dpj here, we're still using the previously state number, right? Because when we use this I minus 1, j minus numbers I minus 1, this number itself will be smaller than j, okay? And if we're looping through, if we're looping through the loops from the smallest to the biggest, and by the time we do the dpj here, we have already calculated this j minus the j minus n nums I minus 1 state, right? Which means we have already considered to use these i's in this case, right? I mean, like I said, if this problem is a complete backpack problem, which means you can use the numbers or items as many times as you want, then this is the correct way. This looping through from the smallest to the biggest is the correct way. But since for this one, it's a 0, 1 backpack problem. For that, we have to use the state from the previously state. We have to use the value from the previously state, which means to be able to be able uh, to make that happen, we have to do it from the small to the biggest to smallest, so that when we calculate dpj here, this dpj minus n nums I minus 1 is still the old value from the previously state, from the I minus 1 state. Okay. Okay, so and yeah, so that's why I have to do a C here, right? And the minus 1 and then minus 1. Okay. Actually, no, yeah. Hmm. And since we already removed the first state, the first one, sorry, since we have already removed the first dimension, so there's no need to do this, right? Since the j is the same, we can simply remove this part. And yeah, I mean here, so here, see here, right? Yeah, basically that's it, right? I mean, I yeah, from we just need to reverse the loop here, and this should just work. Oh, sorry, here. Mm, okay, yeah, yeah, okay, cool, it works. And maybe another small improvement is instead of looping through everything, looping through from C to 0, and we do a check here. We can even do this, right? We can, since we're not going to process anything that's smaller than the nums this number, right? So we just need to do this, right? And we can safely remove this part. Okay, right? We just loop through from C until this number. But anything smaller than this number, we're not interested in that, because that will Mm, yeah, because that will make this j minus this number be a negative value. Okay, this should just work. Cool. Yeah, see, it's improved the speed a little bit more. But anyway, so that's the basic idea of this problem. Just if you guys can don't having problem understanding the space complexity improvement, you can stay with the 2D versions first. Okay, and then if you really and then when you are confident about how this 2D template code works, then you can try to remove the first dimension of the DP array, and then try to do this. But remember, when you do this for the 0, 1 problem, always uh, do the second for loop in the opposite way. Cool, I think that's it for this problem, and another very classic knapsack problem. I hope you guys enjoy watching the video, and thank you so much. All right, stay tuned. See you guys soon. Bye bye.